how about the logarithm one? Anybody got a decent explanation how they're going to think through that? So you use a change of base formula. So I guess we could use our log of base b, log of base a. Okay. So you could use a change of base formula. Does anybody else use something besides a change of base formula?
I made each side the exponent as 5 to the log 5 of 1.5 equals 5 to the x.
Say it one more time slowly. What did you say?
Each side I made the exponent of 5.
Oh, so you exponentiate both sides to base 5? Gotcha. Then those would reduce, so that means 1 to the 1/25th, whoops, has to equal 5 to the x. So what is the exponent you raise 5 to get 1/25th? Yeah, I was hoping that we could do that mentally by using our application of what logarithms find. Logarithms always find the exponent. So this x, whether you do it what David did, by exponentiating both sides to base 5, but that x is the power you raise 5 to get 1/25th. We really need to know the idea behind logarithms. And change of base formula is a good, you've got a lot of information on that too. There's still a really intuitive way that we need to be thinking about logarithms and what they express. They find the exponents that you raise the base to get your answer. In the simplified one, okay, we really like to get rid of these radicals, so we make it x to the 3/5 as a rational exponent times x to the 3/4. Then how do we handle our exponents once we're multiplying like bases? Common denominator, because you must be thinking that you're going to add those exponents. So 3/5 plus 3/4, your common denominator is 20. So that makes this thing from a 3, changes it to a 12, changes the 3 to a 15, which means our exponent is x raised to the 27/20ths. Okay, then probably they're going to convert their answers back into radicals. So it's going to be the what root? 20th root of x to the 27. There are some perfect powers of 20 in there. So we want to write this as the 20th root of x to the, I'm just going to intermediate stage times x to the 7. Which means the 20th root of x to the 20 is just x times the 20th root of x to the 7. That there is your final answer. Okay, that assessment's going to be tomorrow. Take a look at your pump 256. Think of the things that we've practiced routinely here. But don't walk into it cold because bad things happen. Okay, so we're going to work on these things algebraic, and let's take a look at what we have to do with these things. They start this off with a little bit of discussion about vectors in the coordinate plane. So there's some reading here in the textbook that you really shouldn't just gloss over, but you should pay attention to. And we're going to highlight some of those things here, first of all. In 8.1, we found the magnitude direction of vectors of 2 or more geometrically. Since they're not very accurate, we wanted some algebraic approaches. So that's where we're going. A vector OP in standard position. Okay, they're calling out standard position. Where does the initial point need to be? At the origin. Which way are we going to rotate it? Clockwise or counterclockwise? Counter in standard, okay?
Wait, standard equals opposite?
I don't know what you mean by opposite. Standard equals opposite. Standard is just like every angle we've ever had up to this point. Start on the x-axis, rotate counterclockwise. So that's what they're saying this vector OP is doing. It has rectangular coordinates as well, and they can be uniquely described by the coordinates of its terminal point xy. So if we put a vector at the standard in standard position and we rotate it, isn't the terminal point, point P, at a specific point in our coordinate plane? Yeah, it's an x and a y coordinate. And how far to the right would we go? X units. How far up would we go? Y units. So therefore we could say the tip of this is at the order pair x, y. Now are all vectors going to be at the standard position? No, so we're going to want some ways to treat that. So they give us some terminology here and also some ways of writing this. We denote vector OP on the coordinate plane by xy. Now I don't know if you can notice it, but what do you see about the xy
They're in these little chevron things.
They're in the chevron things, sure.
I like that word, chevron.
Chevrons, that's a great way to describe it. Note that x and y are rectangular coordinates of vector OP. For this reason, the chevron, x comma y, is called the component form of a vector. Now they want to make sure that we can distinguish between an ordered pair and the component forms of a vector. If we see this, x comma y, that represents the ordered pair that they're at. It's a single location in space. But if they put the chevrons, x comma y, and that's really magnifying those chevrons, that means they are the components of the vector. And the components are your horizontal displacement and your vertical displacement at right angles to each other. Okay, so first little hurdle here is making sure that we get component form, figure out what is the notation that they're going to use. Chevrons A comma B. Good?
Yeah.
Okay, since vectors with the same magnitude and direction are equivalent, many vectors can be represented by the same coordinates. For example, they're calling out vector P, T, U, or V, and W in this figure all have the same component coordinates. It doesn't always have to be in standard position is what they're saying. But every single one of these vectors are equivalent, and if they are equivalent, you can represent them using the same component form. Not a big deal, right? Just make sure you know that we're going to have multiple vectors that are equivalent to one in standard form. And have the exact same thing. Now this is a really simple thing to do, but they say component form of a vector. The component form of vector AV with its initial point at A and its terminal point at B is given by. So here's our initial point, x1, y1. Our second point is x2, y2. Doesn't this stuff look familiar? X of 2 minus x of 1, y of 2 minus y of 1. What does that remind you of?
Slope.
Slope. Really what you're doing is you're almost finding the slope of these things. But in order to find the horizontal component, you want to know its length. To find the length of its horizontal component, you would simply figure out how long it is between the first point and the second point. Now, it doesn't matter which point you subtract. Yes, order makes a difference. You always want to go terminal to from subtract beginning. Notice how they have these, x of 2 minus x of 1, y of 2 minus y of 1. It is imperative you do it in the correct order. Always subtract terminal minus initial. Because vectors have magnitude and direction. And because direction is important here, we got to make sure we do it in the right way. So then, in the same respects, in order to find your change in your y coordinates, you simply subtract the y coordinates, endpoint minus beginning point. Easy enough?
Yeah.
So here's our first example. It says, find the component form of vector AV with the given initial and terminal points. So in example 1a, the initial and terminal points are given. A is where we start, B is where we finish. I'm not sure if we need a visual representation of this, but what the heck, -2, -7. 1, 2, 3, 4, 5, 6, 7. So we're going to call that -2, -7. This is where we're going to start, and we're going to finish at 6, 1. 1, 2, 3, 4, 5, 6, up 1. This is the vector representation on the coordinate plane. Now they want the component form, which really means they want what two parts of this vector. And the change in x will find your horizontal component, and the change in y will find your vertical component. Yeah, not straight. Is that bothering you?
Oh, it's all good.
It's all good.
It's bothering me.
So the only thing you have to be careful on is make sure that you always take the end point minus the beginning point. So when we do this, we want to take our x's and what one comes first.
Oh, what you think?
Where's your end point? So it's 6 minus -2, comma, 1 minus -7, chevron. So it's really 8, comma, 8. This one has a length of 8, this one has a length of 8, so we can use our component forms of 8, comma, 8.
Big gap between.
All right. Goodness gracious. I don't know why I did either, but just call me out on it, that's fine. 1b. Find the components of 1b. without the geometric representation. What is your endpoint?
-9, -3.
So those have to go first. So it's going to be -9 minus 0, comma.
-3.
Nice. -9, comma, -11. And these are the components of the vector AB. So if you're going to draw a triangle of this, what would it look like?
It's gonna be like,
If I was going to draw the component vectors of this, what would it look like?
Go left 9, down 11.
The left 9, down 11, and supposedly that's where we would end up if... Sorry. Next thing. We just learned about the component form. The component form is nothing more than a formality. They're saying, make sure that you remember that when you see this, it's not a location in space, but it is telling you the direction horizontally and vertically of any vector. Now we're going to talk about the magnitude of the vector, which means it's what? Its length. It could represent its speed. It could represent its strength of the force. But the magnitude of the vector in the coordinate plane is found by using the distance formula. Distance formula finds length. So if a vector v, if v is a vector with initial point x1, y1, terminal point x2, y2, then the magnitude, or the length of it, vector v, is given by, pay attention to this symbol. The absolute value is the magnitude. Magnitude is always a positive unit. How strong is the wind? How hard are you pushing? What speed did you travel? That thing has to be absolute value, so square root of x of 1, yeah, that whole thing there. That's your distance formula. That's not new either, so we're looking like mathematics should be easy on these vectors, and that really is. This little clip down here, if v has a component form, what does it mean if it's a component form? What does a represent? The change of the x's. It tells you how far horizontally your vector is, and what does the b represent? It's changing your y. So they're saying you could have a vector that has component a, component b, then couldn't you find the magnitude that resulted force by taking a squared plus b squared? If it's already a component form, is there a need to find the change in your y's and change of your x's?
No.
Oh, it's already been done. So if it is in component form, it actually makes it a little bit faster. So you can always go to component form, and then once you get to component form, find your length by taking a form of what? What does this look like? Pi theta. And distance formula is pi theta, all the way. So find the magnitude of vector AB with the given initial and terminal points. Okay, this looks a lot like our last one, doesn't it? Last time we found the component form of this. This time we're going to find the magnitude of it. So 1, 2, go down 1, 2, 3, 4, 5, 6, 7. -2, -7. And this one was 6, 1. 1, 2, 3, 4, 5, 6, 1. Do you remember the component form of this from the previous one? Okay, you don't? So what we could do is we could find the component form of this. It was 8, 8. From the time we go to a 6, 1 to a -2, 7, we subtract our x's. 6 minus a -2, that was 8. 1 minus a -7, that was 8. So our component form was 8, 8. If we have a component form of 8, 8, how do we find the magnitude? So the notation of this stuff is going to be relatively important. You probably get by today without knowing a lot of these relationships and what they designate. This represents, what I've written here, is the magnitude of vector AB. It can be calculated by taking the square root of 8 squared plus 8 squared, or 64 plus 64, which is 128. Now, simplifying these is going to take a higher level. Some of you weren't doing that on your ellipse and hyperbola when I said, I don't want messy decimals, I want simplest radical form. But many of you just went to decimals anyway. Not an option here. Square root of 128. What's a perfect square that goes into 128? The biggest one, I think, is 64, because it's 64 times 2. Remember we had two 64s? And 64 is a perfect square, so the square root of 64 is 8. Wow, that shouldn't be a real mind blower. What kind of triangle is this? 1, 1, square root of 2. It's a 45, 45, 90. Did you recognize it?
Whoa!
1, 1, 8 square root of 2. We can calculate some of these by using what we already know about 30, 60, 90s and 45, 45, 90s. On the second one, without a geometric representation, do you want to use a distance formula or do you want to put it in component form first?
Yes.
Distance formula this time. So we're going to take the square root to find the magnitude of vector AB. It's the absolute value, symbols around it. We want to find the change in the x's and square. Now since we're squaring, what does squaring always do to your number? This is the one time you can get messy and it's not going to make any difference, because I don't care if I take x2 minus x1 or x1 minus x2, as soon as you square it, it gets the same number. But if you want to keep it consistent, always take your end point. Here's your end point. Subtract your beginning point. So just like it did last time, it's going to be -9 minus 0. We're going to square it, add to it, -3 minus 8. We're going to square it. So really it's a -9 squared, which is 81 plus an 11, -11 squared, which is 121. And if you add an 81 and a 121, you get 202. Are there any perfect squares in 202? Well, what do you think? You got a feeling there is. Well, if you got a feeling, then you need to go find it. I'm not sure what it is. Does 4 go into it? Does 9? Does 16? 4 does. 4 doesn't go. Your divisibility rule for 4, it's one of those that you might forget, but if you look at your last two digits, does 4 go into 2 evenly?
Oh, it's the last two. I thought.
Yeah. No, just the last two.
Those 3.
If 9's going to go into it, then 2 plus 2 plus 0 has to be divisible by 9. It's not. I don't really see any perfect squares in this, so that's it. Finding the magnitude and doing the components. That's all we've talked about so far. Relatively simple tasks, relatively intuitive tasks, things that we've looked at and seen before, distance formulas, and basically slope. Okay, another component is, how do we add, subtract, and use scalar multiplication of vectors in the coordinate point? And they say it's similar to operation with matrices, but since we skipped the matrices one, we really can't go back and say, well, this is like matrices, this is how you do it, so it's not a big deal. So if vector A is represented by these components, A1, A2, what does A1 represent? I'm pretty sure that's a component. So what is that A1? The first one. That's your change in x. It's really the magnitude or the length of your horizontal line, and the A sub 2 is your change in y, your vertical line. So it's telling you the horizontal and vertical components. And B, vector B, is B1, B2. So you got something that's like, well, there's an A1 here and then an A2 like this. And then you got another one over here that's B1, and then another one here could be B2. And get the deal? They are components of a vector. I just threw a couple there. If they are vectors and k is a scalar, then the following are true. Vector addition. How would you add two vectors? Well, if I wanted to add vector A into vector B, I'd have to do a tip to tail, which means this stuff here would have to go there. And in the end, our resultant vector would go from here to here. How far to the right would we have traveled? A1 plus B1, see what they're doing. And how far vertically would you have gone? Joining the rest of us, everyone? That's not that big a deal either, right? What are they saying that you do in order to add vectors? Simply add your x components together and then add your y components together. Isn't that what that picture is basically showing you anyway? to get your resultant, you would have to go all the way over to here and all the way up. That is an A1 plus a B1 in here, and this is an A2 plus a B2 there. So if we can handle addition, then there's no reason why we can't handle subtraction, because subtracting is adding its opposite. They don't actually do that, but we could think of it the same way. But it's A1 minus B1. So now it's going to be A1, and then we'd have to take B1, and we'd have to, really can't represent it very well, go the opposite direction. Can't give you a good visual representation of that. Subtraction is going to follow just along with like the addition. Subtract your x's, subtract your y's. Scalar vector, scalar multiplication. What does a scalar really do to your vector? What does multiplying a number out in front of your vector do to it? It can make it bigger, or it can make it smaller, or it can change its direction if k is what? Negative. If k were negative, it would force it to go the opposite direction. And then if it's a number bigger than 1, what does it do to your vector? Stretches it. If it's a number between 0 and 1, what does it do? Shrinks it. So k, that scalar multiplication, is either a magnification or reduction of your vector. The only way it can change its direction is by putting in a negative. So operation with vectors. We've got 3 examples here. Find each of the following if w has component forms of negative 4, 1, and y is component of 2, 5, and z is component of negative 3, 0. So they say, what is 4 times w plus z? What does 4 times vector w mean we're going to do?
Negative 2 times 4.
So we're going to take vector w, multiply it by the scalar multiple of 4. Now if we go back up here, all they say to do on scalar multiplication is simply take your scalar and multiply it by each of your components. So that's going to make 4w look like what? Comma 4. It's got to magnify its entire length. Then we want to add to this z, which is negative 3 comma 0. So plus negative 3 comma 0. And what do we do when we add 2 vectors? Add your x component, so that's going to be a negative 19 comma 4. The arithmetic, the algebra on this is relatively simple as long as you get the concept behind it. How are you adding vectors? We're adding the 2 x's and adding the 2 y's. 3b, what does that negative 3 do? What are the 2 things that it does? Changes the direction and makes it 3 times longer. So it's really not a big deal. It's negative 3 times whatever vector components for w are. So that means negative 3w is 12 comma negative 3. So now we have to go 12 years to the right, down 3. That's our resultant vector there, or where we end up. And 2w plus 4y minus z. So let's do the 2w in our heads. What is the 2 times vector w? Negative 8, 2, plus 4 times vector y, so let's do that one. 8 and 20, minus vector z, which is negative 3 comma 0. So how would you do the combined addition and subtraction? Okay, you could take it in smaller steps. Could you do all of them at once? Could you take a negative 8 plus 8 and then minus a negative 3?
Plus 3.
Plus 3. You could do that. What's a negative 8 plus 8? Minus a negative 3 is really going to be 3. That's a 2 and a 20. And then subtract 0, so that's got to be
22.
This should be a nice reprieve from some of the stuff that you had to do. This is relatively simple.
I like it a lot.
Yeah, so do I.
Can we do more drawing and stuff?
It's kind of pretty.
Last thing we'll cover here is this example, and then they'll leave us about halfway through the lesson. But they pick up the second part of this unit on unit vectors. A vector that has a magnitude of 1 is called a unit vector. It is sometimes useful to describe a non-zero vector v as a scalar multiple of a unit vector u. So now u is going to take on a special meaning. When you see this u, it's going to represent a what?
What?
Unit vector of magnitude 1 with the same direction as v. To find the unit vector, you simply divide your vector v by its magnitude. This is how they represent magnitude. That's why all this symbolism that you're going to be seeing in front of you. When you get to 8.3, if you don't know that symbolism, that stuff's going to chew you up. When you see that absolute value of v, that vector, it means its magnitude. So they gave us two ways of thinking about it. We can either take v over the magnitude of v, and this is your component form. Vector v is your components. Or you can take 1 over the magnitude times your component vector v. So find a unit vector with the same direction as a given vector. So if w is 6 comma negative 2, then how would you find the unit vector of vector w? Well, the unit vector would equal the vector w over the magnitude of the vector w. So how do you find the magnitude of the vector w if you're given it in component form? So think about going 6, going down 2. If this is 6, negative 2, we're trying to find the magnitude of that. What is this an application of? Pythag. This is your Pythag idea. And we go back a couple slides. Remember, if it's in component form, look at that. It's just your Pythagorean theorem again. So it's not a big deal if you really understand what these things are asking you to do. You don't need a formula in front of you. You just need to reason. Go 6 to the right, down 2, find this magnitude. That's 36 plus 4, or square root of 40. Now what is w? W is a vector. What are its components? That's why I guess I prefer this 1 over the square root of 40 times the components of vector w, which were 6 and negative 2. A square root of 40 has to be dealt with because you can't leave a square root in the denominator, and there are some perfect squares in 40. What is the perfect square in 40? 4. So that's really the square root of 4 times 10, or 2 square root of 10, which is still trying to get this thing in simplest form. I got 1 over 2 times the square root of 10 times vector w. Take top and bottom times the square root of 10. So it's the square root of 10 all over 2 times 10, which is 20. Okay, so reviewing, we're taking top and bottom times the square root of 10. Square root of 10 times square root of 10 is 10. 10 times 2 is 20. So we've got square root of 10 over 20 times 6. Oops, that's a positive. I'll just change it that way. So what is the unit vector going to look like? We now have a scalar multiple. What is this scalar multiple designed to do? Shrink it down to a size of what length? So it's going to be 6 square root of 10 over 20, comma, square root of 10 over 20, which we could reduce these as well. It's no longer 6 and 20. We could make it square root of 10 over 10, comma. That should be a 20. Sorry. Square root of 10 over 10. Now what is this supposed to represent? A unit vector. If it's a unit vector, what should its magnitude be? So if we were to come back here and double check our work, if we take 3 times the square root of 10 all over 10, square it, add to it a square root of 10 over a 10, square it, it should be a length of 1. So when we square this, 3 times 3 is 9. That's a 10 square root of 10 times square root of 10, which is 10 all over 100. Plus, this is 10 all over 100.
Oh my gosh, it's 1.
That's 90 plus 10. Oh, yeah. Some of you understand it. It's 1. Unit vector. So you can see there's a little bit more work involved in this unit vector, but most of the work came into simplifying a radical. Final example for today, -4, -8. That's our component vector. We're going to find the unit vector. In order to find the unit vector, we want to apply just the simple idea, get rid of your magnitude. If you divide by the magnitude of your vector, you're really going to make it a length of what? 1. It's like 10 divided by 10, 5 divided by 5. You're taking the magnitude and you're reducing it down to a factor of 1. So we want to take and find the unit vector. That means we have to find vector x divided by the magnitude of vector x. If it's in component form, it couldn't be easier. It's 16 plus 64. 16 plus 64 is 80. So it's going to be 1 over the square root of 80 times vector x. Square root of 80, have any perfect squares in it? I think 16's are biggest. Isn't it 16 times 5? 4 goes in there, but then that'll be 20. And that'll be another 4, so it's 16. So this is going to be the square root of 16 times 5, which is, and we want to make that times square root of 5 on top and bottom, so it's going to be the square root of 5 all over 20. We got to take that times our components of vector x, which is -4, -8. And then we'll multiply through by our scalar. This scalar is the thing that's going to bring it down to a magnitude of 1. So it's going to be -4 times square root of 5 all over 20. And then -8 square root of 5 all over 20. Does this sound like what you did in physics at all yet? Did you do anything in unit vectors? Do you recognize it now or not? No, it may not have been a very big priority in physics. So this becomes a negative square root of 5 over 5, comma. They're both divisible by. Right, divisible by 4? Done. And if we took those and squared them, they better add up to 1. Now that probably goes a little bit beyond what I assigned you for today, because today I actually go to 1 to 25 odds. In that 1 to 25 odds, you're going to be writing the components of them, and you're going to be adding, subtracting, and using your scalar multiples. I don't think that gets into your unit vectors yet. So, all right. Today you're supposed to have and turn in 8.1. So before you leave, turn in your 8.1. You can set it on my desk. That's fine. Make sure your name's on it. I'm going to turn this off.